Okay, so the last little type we need to look at then is our inequality proofs. So what I've said here is when we're working with inequalities, there's a few different rules that are important to remember. Now the main ones I'm kind of looking at here are probably this rule is going to come in really all of the inequality proofs that we use. So that idea that if A is bigger than B and if B is bigger than C, then A is bigger than B, then A is bigger than C. Other rules that we'd be using would be this example here and perhaps this example here. Okay, all the rules are important, but those two, or those three, I suppose, are definitely quite prevalent in these ones here. So let's have a look. The first thing we'll notice with inequality proofs is a lot of the time they will give us specific values where they maybe haven't for some of the other proofs. And now they can do this for any of the other proofs, but it's most common with our inequality proofs. And all that it means here is that when I start, I'm not going to start at n equals 1. I'm going to now start at n equals to 2 because they haven't told me here that this is true for all n. They want me to prove that it's true if n is greater than or equal to 2. So 2 is where I'm starting. So I try 2 and I get 9 is bigger than 4, which of course is true. We assume the k. We assume for k. So we assume that 3 to the power of k is greater than k squared. We're going to assume that value. What we want to show now is we want to show the case n equals k plus 1. We want to show that 3 to the power of k plus 1 is greater than k plus 1 squared. And what I'm going to do with this is I'm going to say that's a is greater than c. So I'm using one of those rules from the top there, and I'm calling that a and I'm calling that c, because these are kind of my end goals. This is what I want to show. So we already know from my assumption here, we know that 3 to the power of k is greater than k squared. So if I was to multiply both sides of that by 3, I would get 3 to the power of k plus 1 is greater than 3k squared. And 3 to the power of k plus 1 is exactly the same as I had here. So we'll keep calling that a. There's no reason to rename it. What we will rename, however, is the second one here. And we're going to call that b. So the rule we're using here is that if a is bigger than b, and if b is bigger than c, then a is bigger than c. So we've shown already that a is bigger than b. So we need to show that b is greater than c. We need to show that case. If we can prove that, then we've got our proof. So we're looking to prove that 3k squared is greater than k plus 1 all squared. So let's just do some manipulation here. So k squared plus 2k plus 1. Okay, I'm going to bring things across for myself here and try and rearrange. So 2k squared minus 2k is greater than 1. I'm going to factor out 2k here and I get k minus 1. And by looking at this here, I can test out different values. And all I want to say is 2k times k minus 1 going to be greater than 1 for all the values that I'm looking at? So a good way to look at that is to look at the first value that it doesn't work for. Okay, so when is it going to be equal to 1? So when is it going to be equal to 1? When is that going to be, I suppose, just not greater than? I suppose once we've solved the version where it's equal, then for any other version we can take that as being greater than. Now the other thing we can do is just kind of consider the values. We're only looking at values bigger than 2, so we can look and kind of see for ourselves, does it work if k is 2? Well, let's have a little check. So that would be 4 times 1, and 4 is greater than 1. Does it work if k is 3? Well, that's going to be 12. And we can see now as I increase my numbers, that value is only going to increase, because looking at it generally there, we can kind of get a sense of maybe when it doesn't work. Okay, so somewhere between probably 1 and 2 is where it's going to give me an exact answer of 1. So we can say that this here is true for k greater than or equal to 2, which is what we have. So therefore, our little closing statement is true for n equals 2. If true for n equals k, then that implies it's true for n equals k plus 1. and therefore true. This time we have to be careful, so true for n greater than or equal to 2. Not necessarily for all n, but so long as it's bigger than 2. So that's the kind of slight difference there. Let's look at another example of that then. So we're proving by induction that n squared is greater than 4n plus 3. So for n greater than or equal to 5. So first step this time is going to be that n is 5. 5 squared, is that greater than 4 times 5 plus 3? Is 25 bigger than 23? And it is, of course. Next we want to assume my n equals k. So I assume k squared is greater than 4k plus 3. And I need to show now that n equals k plus 1. So is k plus 1 squared greater than 4 times k plus 1 plus 3. So we want to show, is this case true? So following the same rules we had the last time, this is going to be a now, and this is going to be c. And what we might do actually before we even label them is just work it out a bit more properly. So k squared plus 2k plus 1 greater than 4k plus 7. So this is a, and this is c. We already know k squared is greater than 4k plus 3. Okay, we already know that. So if I want to, I suppose, adjust this now to match what I'm trying to show, what I need to look at is this 2k plus 1 part. So if I add that to both sides of my inequality here, that's not going to change my inequality, but it's going to make it more like the one that I have here, meaning that this will now be a and that this will now be b. Let's just simplify, I suppose, particularly that right hand side there to get 6k plus 4. We just need to now prove that b is greater than c. We need to show that b is going to be greater than c. So b is 6k plus 4, and we need to show that that's bigger than 4k plus 7. So I get 2k is greater than 2k is greater than 3, and I get the k is greater than 3 over 2. I get the k is greater than 3 over 2. So it works when k is bigger than 3 over 2. And of course what we know is that that means it's going to be true for my n greater than or equal to 5, which is what I want. So therefore we can say it's true when n is 5, if true for n equals k, then it's true for n equals k plus 1, and therefore it's true for n greater than or equal to 5, where n is an element of there. Okay, so again, the same idea happening the entire time here. Okay, those same little adjustments or those same little tricks kind of happening all the way along. Let's look at another example, I suppose. So prove by induction that 1 plus x to the power of n is greater than or equal to 1 plus nx for x greater than minus 1. So they haven't given us any particular value of n here, so let's just start with 1. So is 1 plus x greater than or equal to 1 plus 1x? And of course it is. We assume the k stage and we need to show for n equals k plus 1. Okay, so this is what I'm looking to show here. I'm looking to show this version, and what I can do here, I suppose, is I can simplify this a little bit, particularly that first part, if it serves me to do so. It's just a matter of, I suppose, deciding whether it does. So let's just go with A and C for the time being, and if we need to, we can simplify that down. What we know already is we know that it's true when n is equal to k. So we know that this expression was true. And in order to match up that expression to this one up here, I'm going to need to multiply this by 1 plus k. And I have to then do that that, or 1 plus x, and I have to then do that to both sides. So I get overall 1 plus x to the power of k plus 1 is greater than or equal to, and I can multiply that out there fully if I want to. Okay, I can multiply that out fully. So 1 plus x plus kx plus kx squared. So what I now have here is that a is greater than b. So we need to show that b is greater than or equal to c. Okay, so we need to show this. We need to show that b is greater than or equal to c. So taking those examples here, 1 plus x plus kx plus kx squared greater than or equal to 1 plus k plus 1 x. Okay, let's do some simplification here. So 1 plus x plus kx plus kx squared greater than or equal to 1 plus kx plus x. So I get kx squared is greater than or equal to 0, which of course is true for all n. Of course, it's true for all n. So therefore, what we've shown, okay, and I suppose it's the one maybe part that we've been missing out here, is what we've shown is that a is greater than or equal to b, which is greater than or equal to c. Okay, and that's what we've been aiming to show in each of them. And what that means is that a is greater than or equal to c. And that is true for n equals 1, if true for n equals k, then true for n equals k plus 1. Therefore true for all n. Okay, so this little step here, and particularly even we could write in the actual versions of those as well. So the 1 plus x to the power of k plus 1 being greater than the 1 plus kx plus x plus kx squared being greater than my c, which was my 1 plus kx plus x, and using that to prove the rest of it. And that is written out in your notes as well, a bit more, I suppose, thoroughly, perhaps than I'm writing it here, but just to get the general sense of it. So really that last line, probably one that we should be including the whole way along there as well. So writing in this line here as well of a is greater than or equal to b, which is greater than or equal to c, then that implies that a is greater than or equal to c. Okay, and that's the general rule that we're using the entire time here with these inequality proofs. Okay, so with our inequality proofs, then there's a second type here where we have factorials. Okay, where we have some factorials. And a factorial is just where we multiply all the natural numbers less than whatever the natural number that we have is. So say we have 6 factorial, that's going to be 6 times 5 times 4 times 3 times 2 times 1. Okay, and we would see this in probability. So it's important to just be aware of what that factorial notation is. Okay, so that's just important to be familiar with. What it also means for us here is that we can make use of this little trick that we have here. So n plus 1 factorial is the same as n plus 1 times n factorial. And what that kind of comes from is 6 factorial is the same as 6 times 5 factorial. And 5 factorial is the same as 5 times 4 factorial, and so on and so forth. So we can make use of that then in these proofs. So again, it's still an inequality, so there's no guarantee they're getting us to start at 1, and here they're not. They're saying start at 5. So let's try it out for 5, and we'll see how this differs from some of the other ones that we've done. So we've got 6 factorial is greater than or equal to 3 to the power of 5. So let's see if that is the case. Calculator. So we have a factorial button on our calculator here. Again, it's just an exclamation mark. Do you think I can find it? I think so. There we go. 6 factorial 720, and is 720 greater than or equal to 3 to the power of 5, 243? It is, of course. So that's true. Okay, so that's true. Okay, without us really having an awful lot of proving to do there, I suppose. So let's assume the k case. So we're assuming that k factorial is greater than or equal to 3 to the power of k. And then we need to show that it's true for n equals k plus 1. So I want to show that k, or not k, sorry, this should be k plus 1 here. K plus 1 factorial greater than or equal to 3k. I want to show that k plus 1 factorial is greater than or equal to 3k. Okay, that's essentially what I want to show. So obviously k plus 2 factorial greater than or equal to 3k. And again, similar to how we've done the last ones, we're going to label this as A and we're going to label this as C. Okay, what we know already, so we know that n equals k was true, and that was that k plus 1 factorial was greater than or equal to 3 to the power of k. And again, I want to maybe make that fit with the other example that I have here, fit with the one I want to show. And the only difference is that instead of stopping at k plus 1, I'm multiplying it by k plus 2, bringing us back to that idea of 5 factorial multiplied by 6 would give me 6 factorial, because it's the next number in the line. Of course, I need to multiply both sides if I'm going to do that. And that overall is going to give me k plus 2 factorial being greater than or equal to 3 to the power of k times k plus 2. And this is now my A being greater than or equal to B. So we need to show that B is greater than or equal to C. And that then will lead us to an induction to show that A then is greater than or equal to C. So we essentially need to show that 3 to the power of k times k plus 2 is greater than or equal to 3 to the power of k. Okay, and I mean, the first thing I suppose we can say there is, or sorry, I should have k plus 1 here. That makes sense. K plus 1. Okay, so that's essentially what we're trying to prove here. 3 to the power of k times k plus 2 is greater than or equal to 3 to the power of k plus 1, of course. Okay, so trying to manipulate this, I suppose, to some extent here. What we could do is rewrite the left-hand side as 3 times 3 to the power of k. Now what I can do here is I can divide both sides by this 3 to the power of k. 3 to the power of k is going to be positive. I won't have to change my inequality sign or anything like that. And I get k plus 2 is greater than or equal to 3. Which means that this is true if k is greater than or equal to 1. And of course, we know that's going to be true as my values of n start at 5. So I know it's definitely true. So what we've shown now is that A is greater than or equal to B, which is greater than or equal to C. Okay, so reminding ourselves of that, we're saying that k plus 2 factorial is greater than or equal to 3k times k plus 2, which is greater than or equal to 3 to the power of k plus 1. And that implies that k plus 2 factorial is greater than or equal to 3 to the power of k plus 1, which is our A being greater than or equal to C. And again, my little closing statement doesn't change. It's true for n equals 1, if true for n equals k, then it's true for n equals k plus 1, and therefore true for n greater than or equal to 5. Okay, so slight differences, but a lot of the same thing coming in with our inequality ones there. The only difference, I suppose, being you just need to make sure that you understand that factorial notation, that you're able to kind of make use of that and exploit that. We'll look at one last example then. We need to prove again for n equals 1 first of all. So that's proving that 1 factorial is greater than 2 to the power of 1 minus 1, or not 1, sorry, we're starting at 3 as the question says. So let's make sure we do that. So is 3 factorial greater than 2 to the power of 3 minus 1? Well, 3 factorial is 6, and this is 2 to the power of 2, which is 4. So that is true. If we assume my n equals k then, we're saying that k factorial is greater than 2 to the power of k minus 1. Now we want to show the k plus 1 version. We want to show that k plus 1 factorial is greater than 2 to the power of k plus 1 minus 1. Okay, k plus 1 minus 1. So that's what we're looking to show here. That's what we want to show overall. So if we make that connection, we'll call this A, we'll call this C, the same connection we've been doing all along here. we know that the n equals k was true, so we know that k factorial is greater than 2 to the power of k minus 1. And again, I'm looking at the same idea as before. I'm going to multiply this side by k plus 1 to get k plus 1 factorial, but doing that to this side as well. So I get k plus 1 factorial is greater than 2 to the power of k minus 1 times k plus 1. And again, what we have here now is this is a, but this is now b. So we need b to be greater than c. We need b to be greater than c. Okay, so let's have a look. 2 to the power of k minus 1 times k plus 1. Is that greater than 2 to the power of k plus 1 minus 1? Okay, there's a reason now I maybe haven't multiplied that one out fully, and it's because we're going to make use of the same kind of trick that we had the last time. So factoring out 2k to the power of minus 2 to the power of k minus 1 gives me 2 to the power of 1 here. I can divide across by that 2 to the power of k minus 1 term, and I can get that k is greater than 1. And of course this is true because we already know that my values of n, or my values of k, would start at 3. So therefore, we've shown a is greater than or equal to b, or is greater than, I suppose in this case, a is greater than b, which is greater than c, and that implies that a is greater than c. Okay, and that was what we were trying to prove. K plus 1 factorial is greater than 2 to the power of k minus 1 plus 1, which is essentially just 2 to the power of k. Okay, and finally just my little statement. So true for n equals 1, if true for n equals k, that implies it's true for n equals k plus 1, and therefore true for n greater than or equal to 3, where n is a natural number. Okay, so there's a fair bit in the inequality proofs there, and it does all kind of boil back down to this idea here every single time. But the little tricks that you have, I suppose, or manipulations for proving those can be a little bit tricky. So it's just something to watch out for. Now, a lot of the times they are similar to these sort of example ones, and you'll see that in the kind of exam question ones that you have there. And as I said with the previous ones, I'll do a separate video on the exam questions then. Just if that's all that you kind of want to run through, if you're happy with the example ones, you can just watch that one.